Okay. In the last class, I had stopped at probably the V number. Means I did not talk about the V number. V number means it is a parameter that is used in estimating the number of rays or the number of modes that are propagated. So in this lecture, let us start with this particular parameter. In order to understand this, it is good if I say something about the modes of propagation. Modes of propagation is simply the number of rays that are propagated in an optical fiber. We can say in simple language in that way. You know that the optical fiber will be having a diameter of the order of a few micrometers, so that very small amount of light will be propagated through the optical fiber. That is the reason why the acceptance angle and the condition for laser propagation in the optical fiber is very important, that we discussed in the last class. Since the diameter is too small, certain number of rays can be considered to be propagated in an optical fiber. So modes of optical fiber means the number of rays that are propagated in an optical fiber. Just a minute. Okay. In order to calculate that number of rays that are propagated in optical fiber, this is the equation. V equal to pi d by lambda numerical aperture is multiplied. Numerical aperture was defined in the last class. It is the, in mathematical form, sine of the angle of acceptance. And angle of acceptance was defined as the maximum angle of incidence for a ray of light at the core cross section, such that its refracted ray can undergo total internal reflection at the core clad interface. So that was the acceptance angle, and the sine of that one means sine theta naught was the numerical aperture. It measures the ability of an optical fiber to support or to guide light ray to propagate. Here in this equation, d is the diameter of the core of the optical fiber. You had understood that if this is the core of the optical fiber, this is the clad, this core will have a diameter. This diameter is taken to be d, and the light ray that enters into this core, if you think this is the light ray, it will have a wavelength that is lambda. So now it is clear that d is diameter, numerical aperture is known quantity which we discussed in the last class, and lambda is the wavelength. And numerical aperture was calculated in the last class. It is square root of n1 square minus n2 square. So this is the expression for numerical aperture. In case the surrounding medium is air, n0 will be taken to be equal to 1. In general, n0 is different from 1. And this is the equation which gives us a parameter known as V number. This V number is required to calculate the number of rays that are propagated in an optical fiber. Technically, it is called number of modes, because a ray of light does not physically exist. It is an imaginary path that we consider in order to represent the direction of the light propagation. Or you can say ray of light is the lowest quantity of light that propagates in the narrowest path in a direction. That is the ray of light. Such rays of light are propagated in an optical fiber, which can be approximated using this equation. It doesn't give exact value, but it is an approximation. So n is equal to v square by 2. This measures the number of modes or number of rays that are propagated. You just need to remember this equation for v and for n for calculating these parameters in some problems. So based on this number of modes as well as the refractive index profile, means the variation of refractive index with respect to the radial distance of the core and clad. Based on these two quantities, it is possible to classify the optical fibers into three categories. One is step index single mode optical fiber, step index multi-mode optical fiber, and graded index optical fiber. This is in short called GRIN optical fiber also. GRIN, GR indicates graded, in represents index, graded index multi-mode optical fiber. Let us discuss one by one. Step index single mode optical fiber is the one which supports only one light ray to propagate. You can observe from this diagram. Only one ray of light you are observing here. This light ray is undergoing total internal reflection within the optical fiber. And this light ray is considered to be of single mode. It is because its area of cross section is too small, or diameter of the core is very small. It is of the order of 8 to 10 micrometer. And diameter of the cladding, this is the cross section of the optical fiber, 60 to 70 micrometer will be the cross diameter of the clad, whereas for the core it is 8 to 10 micrometer. And refractive index will be varied in this way. It is varying in such a way that the refractive index is constant throughout the body of the core. This is the core. Within this core, refractive index is constant. It may be 1.6, for example. That 1.6 is the refractive index at every point. Similarly, here the refractive index of the clad is also constant. At this core clad interface, the refractive index falls down to the value of the clad. If it is 1.6 for the core, and for the clad, this will be around, for example, 1.59 or 1.58. So this is true even on the other side. Here 1.59, this is also 1.59 refractive index. So this is known as refractive index profile. Here this line indicates that at the rim of this particular clad, the refractive index falls to the value of the surrounding medium. If the surrounding medium is air, its refractive index will be 1. So that refractive index falls from 1.59 to 1 sharply. That is why refractive index profile is shown to be in a step form. Constant refractive index in the core, constant refractive index in the clad, but values are different. Since this refractive index profile looks like the steps, it is called step index. Step index term is appeared because of this reason. And it is called single mode optical fiber because it supports only one mode of light ray to propagate, or one light ray to propagate through it, because of its very small diameter. So this is about the step index single mode optical fiber. It is very advantageous for long distance communication, but main disadvantage is that manufacturing cost is very high. It is very costly because we have to manufacture the optical fiber with very, very narrow diameter of the core. That's why cost is too high. Manufacturing cost is too high. And the second one is the step index multimode optical fiber. The difference between the single mode optical fiber and multimode is that it can support higher number of light rays to propagate. You are observing here. A higher number of light rays are propagated. What is the reason? Reason is that the core is made to have higher diameter. You can observe here that 50 to 200 micrometer is the diameter of the core. And 100 to 250 micrometer, they are the typical values. These are not the exact diameters of the core or the clad, but these are the typical values. So these values will vary according to our applications or requirements. And as usual, the refractive index of the core remains constant here also. Let us say 1.6 everywhere. Everywhere it is 1.6. and refractive index falls to the value of the refractive index of this clad, whose refractive index is usually smaller than that of the core. Therefore, obviously, this comes down to the refractive index of the clad. It may be 1.59 or 1.58. And again, at the rim, since the surrounding medium is air, if it is assumed as air, its refractive index falls down to the value of the refractive index of the air. It is 1. So this also looks like the steps again. Therefore, it is step index. Multi-mode, because it supports multi number of rays or a number of modes to propagate because of the higher area of cross section. The main disadvantage of this particular optical fiber is that it is suffered from an optical phenomenon known as intermodal dispersion. Intermodal dispersion means it is the phenomenon in which, due to dispersion within the body of the core, different rays of light will reach the receiving end. This is the receiving end. The different rays reach the receiving end at different instants of time. They cannot reach the receiving side at the same time. That is the main drawback of this particular optical fiber. Let me tell you what is the reason. You know that the refractive index or the velocity of the light, let us say c, of course c is the speed of light in vacuum. Let me take v, velocity of light in the case of a medium. That velocity is inversely proportional to refractive index. This is well known fact. If the refractive index is high, the velocity of light is smaller. For example, you know that velocity of light is 3 into 10 power 8 in the vacuum, whereas the velocity of the same light in air is little smaller, and in a glass it is even smaller. It may be around 2 into 10 power 8 meter per second in a glass, because glass has higher refractive index, around 2 or 1.5, depending upon the material. So higher the refractive index, lower will be the velocity. And here different rays are traveling with the same velocity because refractive index is constant. All the rays travel with the same velocity or same speed, but problem is that they are traversing different distances. For example, this light ray is undergoing less number of total internal reflection. For example, within this much length itself, this light ray is undergoing only 2 total internal reflections. And if there is a light ray which can undergo higher number of reflections like this travels longer distance because its zigzag path is higher. It travels longer distance as compared to the other light ray that is undergoing less number of reflections. So the light ray that is traveling longer distance reaches the receiving end later, and the one that is undergoing less number of reflection reaches the receiving end earlier. You just take a simple example. If we have to go to a place like, for example, Bangalore from Hassan, there are various routes. You can go via Chandrayapatna, Kunigal and Nelamangala, and it is possible to go via Tipturu, Tumkuru and Bangalore also. But the distance that we travel via Tumkuru is longer than the distance that we travel via this route, Chandrayapatna Kunigal route. If the two buses traveling with the same speed but in the 2 different routes, they cannot reach Bangalore station at the same time. So that is the similar case that is happening here. If a light ray travels longer distance, it reaches the receiving end later, and the light ray undergoing less number or traversing shorter distance can reach earlier. So different rays reach the receiving end at different instants of time. This is the intermodal dispersion, which leads to noise. If a person wants to hear the voice of the other person who is speaking at the transmitting side, then he cannot listen to him with the clarity. That is the drawback of this optical fiber. That's why this optical fiber is used only for short distance communication, because shorter the distance, intermodal dispersion will be smaller. Longer is the distance, higher will be the intermodal dispersion. That is the main drawback. But manufacturing cost is less because of the higher cross sections. Manufacturing is not so difficult. That's why cost is low. And the third one is graded index multimode optical fiber. This particular optical fiber was developed, in fact, to suppress the intermodal dispersion. So what was done? Only change or the difference from the second type of optical fiber, that is the step index multimode optical fiber, is that core is made to have variable or gradually changing refractive index. That's why it's called graded index. If the refractive index is highest at the center, let us say 1.6, next immediate point is made to have 1.58. This point will be made to have 1.56. Core clad interface, at this core clad interface it is made to have 1.55, and then it will be made constant. So refractive index of the core decreases from center towards the core clad interface, this interface, on both the sides this way. So here also, so it is variable. Refractive index is highest at the center, lowest at the core clad interface, and it decreases along the radius, that is along the radial distance towards the rim, or I can say interface between the core and clad. But clad is made to have the constant refractive index, as I mentioned earlier. That's the reason why refractive index profile looks like this one. It is not showing the steps, but it is showing the gradually variable refractive index. Hence it is called graded index multimode optical fiber. And the dimensions remain same, 50 to 200 micrometer, as we looked in the case of the second one. And here, the number of rays that are propagated through the optical fiber, again more than 2. A number of rays are propagated, hence it is the multimode optical fiber. How intermodal dispersion is suppressed, that's what we need to importantly understand. Let me again tell you that velocity is inversely proportional to refractive index of a medium. If that is true, in the region of higher refractive index, means in the central part, you are observing that there are few rays, these rays traveling only in the central portion. Why? It is because the light ray is refracting at every point within the optical fiber core. If you think this is a glass, when a light ray is made to incident upon it, it gets refracted this way, it bends. If you add one more glass plate, it will again refract. If you add one more, that will again refract. So what are you observing? At every point there will be the refraction. Hence there is bending of light like the curvature. Here every point has different refractive index, so obviously the light ray will be bending at every point. If the light ray enters at the smaller angle into the core, then it cannot reach the interface. It will simply bend here itself and goes in the interior portion of the core. And the other rays which incident at the core cross section at a higher angle but smaller than theta naught, that is acceptance angle, it can even touch the interface. Such a ray, this ray is traveling longer distance, but its most of the portion is in the region of lower refractive index. This is the region where the refractive index is smaller. This is the region of higher refractive index. Majority part of this particular ray is propagating in the lower refractive index region. Therefore, it goes faster in an average. This is faster than the rays that are propagating within the core, means within the interior of the core. So this light ray will travel shorter distance but go slow because the refractive index is high in this region. So some rays are traveling smaller distance but with smaller distance with lower velocity, and other rays are traveling longer distance with higher velocity. Of course, this is with lower velocity, because high refractive index region, these rays are traveling with lower velocities and traveling shorter distance. These rays are traveling longer distance because of with the higher velocity. So let me take the same example again of the buses. Two buses going to Bangalore from Hassan, one via Tumkur, the other one via Chennaraipatna and Kunigal. So the two buses, the bus that is going via Tumkur may be traveling with the speed of 100 km per hour. Another bus which is going through Chennaraipatna may be traveling with the speed of 70 km per hour. So the bus which is moving with the speed 70 km per hour travels smaller distance. The other one which is going through Tumkur is traveling longer distance but with higher velocity. So there is a chance for both the buses to reach the receiving end, that is the bus station, at the same time. Similarly, here, although there are a number of light rays, they can reach the receiving end at almost same time. This is how intermodal dispersion is reduced. Of course, it cannot be completely eliminated due to the distance, long distance communications, but it is possible to suppress. It is smaller, means intermodal dispersion is smaller as compared to that in the case of the step index multimode optical fiber. Since the intermodal dispersion can never be completely eliminated, this optical fiber is used mostly for the intermediate distance communications. For very long distance communication, for example, between two countries or between two cities within a country, like between Delhi and Bangalore, the distance is around 2000 km. For such communications, optical fiber, single mode optical fiber is very essential, because there should not be any intermodal dispersion. Since it supports only single ray to propagate, obviously there is no question of intermodal dispersion in the single mode optical fiber. But in the case of the other one, means in the step index multimode and graded index multimode, intermodal dispersion is there, hence they cannot be used for long distance communications. And step index multimode cannot be used for both the long distance and medium distance communications because of very high intermodal dispersion. But this one, graded index multimode optical fiber, has reduced intermodal dispersion, hence it is used, or it is considered for the applications for short distance communications, like between the two cities within a state, like between Bangalore and Hassan and Chennaraipatna, Hassan and Sakleshpur. For such small distance communication, it can be used. And the other one, the step index multimode optical fiber, can be used only very short distance communication, like for example, networking of the computer cables, or networking within a building or within a mall or a complex, that can be used, right? That completes the theory part of the optical fibers. You just study the content which I described in my lectures. Don't study anything else. But you need some problems. So let me take 10 minutes. Now it is 9:24. I try to finish it as early as possible. Before going to that, let me take your attendance again. Right. I was talking about the problems. Here I have given that a laser device emits a beam of wavelength 632.8 nanometer with output power 5 milliwatt. Calculate the number of photons emitted per second by the device. Here, in order to understand this problem, it's good if we go through the data. Here you are observing that the wavelength is given, which is 632.8 nanometer, and output power is given to be 5 milliwatt, and we need to calculate the number of photons emitted per second. You know that energy of one photon is given by hc by lambda. from the theory of black body radiation, you have understood this. H nu in terms of frequency, hc by lambda in terms of wavelength. This is for one photon. If there are n number of photons, then equation will be nhc by lambda. That's the equation. And if nhc by lambda is the expression for energy of n number of photons, then that energy divided by time gives you the power. Because power is given in the problem, power is given by energy per unit time. So that if you substitute the expression for energy, that is nhc by lambda, you are observing here in the place of E, I have written nhc by lambda, T is here. And on simplifying this equation, P is equal to nhc by lambda T. If you remember this equation, it is enough for solving the problem. Just to help you understanding how to get this equation, I have told about this equation, that is number of one photon, number of n photons, etc. Remembering of this equation is enough for you people. So you substitute the values by rearranging the equation, because we need to calculate n. You will get 1.59 into 10 power 16 per second. Lambda is given 632.8 into 10 power minus 9 because it is nano. T is 1 second because we are calculating number of photons per second. Therefore, time should be 1 second. Power is given 5 milliwatt, 5 into 10 power minus 3 watt. H is Planck's constant, 6.625 into 10 power minus 34 joule second, and speed of light is c, 3 into 10 power 8. And I give you this problem as an assignment. You try to solve it on your own. The answer is given. I will upload the video later, wherein you can find this problem again. You need not note it down now, so that you can solve it. I am taking up the next problem. And in this problem, data given is wavelength, that is 632.8 nanometer, input power, number of photons emitted per second, and output power. Here, the input power in the case of solid laser device, input power is 100 milliwatt to produce laser of this wavelength, such that this many number of photons are emitted in 1 second. So time is 1 second, T. I have not mentioned here, but in the formula you have to take T equal to 1 second. Estimate the output power and percentage power converted into light energy. So the same equation as I described in the first problem, power is nhc by lambda T. Number of photons is given, H, C are constants, we know them. Lambda is 632.8 nanometer, T is 1 second. If you substitute, you will get the answer 0.01 watt. Use this value to calculate percentage efficiency. Efficiency is always output divided by input. So output power divided by input power gives you the efficiency. If you multiply 100, you will get percentage efficiency. We have got 0.01 watt as the output, and 100 milliwatt was given in the data itself. On substituting, you will get this particular answer. 10% is the answer for this problem. And in the other problem, an active medium of a laser device has a wavelength separation of 1 micrometer between its ground state and excited state at 300 degree Kelvin of temperature. Determine the ratio of population of atoms in the upper state to that in the ground state. That means when we supply energy, the electrons will go from lower energy level to higher energy level. And while returning to ground state, that will emit a radiation of certain wavelength that is given. 1 micrometer is given. So wavelength is known, and the temperature at which the radiation emitted is also given. You just have to calculate ratio of population. And while deriving the expression for the energy density of a laser beam, I had taken the Boltzmann factor, which is N2 by N1 is equal to e power minus h nu by kt or hc by lambda kt, because nu is equal to c by lambda, because c is the product of wavelength and frequency. And here k is known as the Boltzmann constant, whose value is 1.38 into 10 power minus 23 joule per degree Kelvin. T is temperature, that is given 300 degree Kelvin. And lambda is also mentioned, 1 micrometer, 1 into 10 power minus 6 meter. H, 6.625 into 10 power minus 34. C, 3 into 10 power 8. Substitute all values and get this answer. 1.365 into 10 power minus 21. Unitless quantity because it is a ratio of numbers. And a similar problem is given here, but Only difference is N1, N2 by N1 is given. Ratio of population is given. N2 by N1 is given. Temperature remains the same. It is same as the previous problem. We have to calculate lambda. It seems to be just rearrangement of the previous problem. It is just rearranged. I have just changed the data. Formula again remains the same, and that is Boltzmann factor formula. Ln n2 by n1, you apply the log base e on both sides. Since exponent is here, log base e is very essential to solve this problem, not the log base 10. Of course, log base 10 also can be taken, but finally you have to convert that into log base e. Instead of that, you take directly the log base e, so that log e power something gives you simply that power only, because log e power x is nothing but x itself. That is the simple thing, mathematics. X log means log base e. I am talking about log base e of e power x is equal to x. I am applying that one here, so that you are getting minus hc by lambda kt. Ln n2 by n1 is here. Rearrange the equation because we need to get the value of lambda and substitute the values given. Logarithm of n2 by n1 you have to take, so that you will find out this answer, 696 nanometer. And now this is the problem about the optical fibers. Refractive index of the core and clad are given. We have to calculate the numerical aperture and the acceptance angle. And data given are refractive indices n1 and n2. Means refractive index of n1 of core is generally taken as n1, and for clad it is n2. Numerical aperture and acceptance angle will be calculated. This is the equation, numerical aperture equation. N1 is here, N2 is here. N0 should be taken as 1 because it is not mentioned in the problem. So we are assuming that N0 is equal to 1, which is for the air medium. So that numerical aperture will be 0.244. And acceptance angle, we know that numerical aperture is sine of angle of acceptance. That is sine theta naught. Therefore, theta naught is sine inverse of NA. NA is here 0.244. So sine inverse 0.244 gives you 14.1 degree. And a similar problem is here. Refractive index is given again. Numerical aperture of acceptance angle, fractional index difference. That is the additional calculation to be done. So it is similar to the previous problem. Just use the value of n0 equal to 1. Since it is not mentioned here in this problem, we have to, oh yeah, it is mentioned. You can observe here that the fiber is placed in air. It's clear. So that n0 is equal to 1. This one. And n1 minus n2 square. Values are here. Substitute and get the value. And then acceptance angle. You can use this equation. Sin theta naught is acceptance, I mean numerical aperture. So theta naught is sine inverse of 0.39, that gives you 23 degree. And fractional index change is n1 minus n2 by n1. This is the equation for that refractional index change. n1, n2, n1, everything is here. Substitute and get the answer, 0.032. And numerical aperture of an optical fiber is 0.2 when surrounded by air. We have to calculate this is the important thing. It is surrounded by air. Determine the refractive index of its core if the refractive index of the cladding is 1.59, and find the acceptance angle when the fiber is in water. This is important. It is in water. Assume the refractive index of water to be 1.33. So like data, what is given? Numerical aperture in air is given. Numerical aperture in water is not given. Refractive index of water is given. Refractive index of cladding is given. Refractive index of core is not given in the problem. So that you have to calculate the refractive index of the core as well as the acceptance angle in water. So numerical aperture equation is this. Since it is in air, n0 is not mentioned in this equation. So you will get n1 from this equation on rearranging. And then numerical aperture in water. Since n0 is not equal to 1 for water, I have to consider this in the numerator denominator. N1, N2. N1 is known from this calculation. N2 is given. N0 is also given. N0 is nothing but NW here, because refractive index of the surrounding medium is water. Therefore, NW should be taken 1.33 in the place of N0. So you will get this numerical aperture value, and you can calculate theta naught as we did in the previous problems. And in this problem, we have to calculate the number of modes using the refractive index of the core and the cladding. Core and clad refractive indices are given, core diameter is given, wavelength is given, because V number requires diameter, wavelength and numerical aperture. So that we need numerical aperture expression, square root of n1 square minus n2 square. If it is not given anything about n naught, you just assume, yeah, it is given, placed in here, it is clear. So n naught is equal to 1. N1 is given 1.55. This is N2 is 1.5. D is 40 into 10 power minus 6 micrometer. 40 micrometer. So it is 40 into 10 power minus 6 meter. And wavelength is given 1400 nanometer. Substitute and get the value of V. And then N is V square by 2. Calculate this one. And I give you an assignment. Similar problem. You calculate. What to calculate? Calculate the wavelength of the laser used for communication. So these are the different types of problems which may appear in the examination. Just learn these types of problems or similar problems. They are enough. And this completes the lectures on all 5 modules.